Hey guys, hope things are going well. In this particular lecture video, I'm going to take a look at the last part of Unit C, C8 and 9. And then just remember that there are problems after that, additional problems for you to work through on page C10 and C11. So let's take a look at Spearmans Correlation coefficient. So the problem that we were working through before was where you had two interval scale variables, and we calculated an R, and that's called Pearson's R. So that's the normal R that you would calculate here. But Spearman's R, and it's easy to get them confused because they sound very similar to each other, Pearson's R is used when you've got a problem with normality or that one or both of the variables are ordinal in nature. So on this particular page, this is C8, page 142, it says that you want to use Pearson's correlation if you can when you have two interval scale variables, like height and weight or age and push-ups, but the variables need to pass the normality test, and that's for both the x and the y. So just as an aside, I'll be putting up another video in the Business 307 Labs section, and what it will show you is how to use a template that I made for you called correlation and SLR, or simple linear regression. And what you'll do is you'll just plop the x and the y in there and then turn to the normality test page. And you can see the results of the Anderson-Darling normality test, and there's a separate test done for both for the x and the y. Now, if the n's are at least 30, you don't have to worry about it, but if the n's are less than 30, and if the normality test fails, then you should be using the non-parametric equivalent, which is the Spearmans Correlation coefficient test. It's the same kind of idea as when we used the Kruskal-Wallis instead of the ANOVA when normality failed. The other reason that you would use a Spearmans correlation coefficient, as I mentioned, is if one or both of the variables are ordinal in nature. So if you're looking at something like the ratings or the rankings in two different cases then, so an x and a y, x ratings and y ratings or something, then that's when you would be using then a Spearmans correlation coefficient. So taking a look on page C8 here, what we've got here is that we've got a slightly different formula here for calculating the R, and I usually put a little subscript down here which is RS to say that this is a Spearmans R instead, and the rho in the hypothesis test has a little s, so it's Spearmans rho. Now if you leave the S off, I'm not going to jump up and down on an exam. That's not a big problem here. But that's how we distinguish between the two. So the formula is a little goofy. It looks like this, and we'll get to that in a moment here. And I'll show you how to work through this. You want to read this, of course, as you go through. There is a note right here that says, for samples that are less than 10, there's actually a special table that you can use, and we're not going to use that because practically the data sets that you'll be using have n's greater than 10, and so you can use this formula here. And so even on an exam, although you might end up with very small n's, so it might be less than 10, I still want you to use that one because practically you would be dealing with correlations or n's which are larger than that. All right, given that, let's take a look at a problem here. So this is on page C9. The Edmonton Windsurfer Club fleet number 11-134C, which actually was the fleet that I was part of. We used to race every Wednesday night. Holds a summer series of windsurfer races, or at least they did back in the 80s. At the end of the summer, the windsurfers are ranked according to their ability. So 1 indicates the highest rank. The ranks for 10 racers over 2 years are shown below. is there a consistency between the ranks? That is the first year a good indication of rankings in the second year? So notice first of all that the data are ordinal in nature. They're ranks. So we shouldn't be using a Pearson's test. We should be using a Spearmans correlation test. Now I don't have a lot of room down here, but let me write your HO and your HA. So HO is going to be that your row, this will be a Spearman's row, is equal to 0, that there's no relationship from one year to the next. Against the alternative that there is a positive correlation. So if you go back to the way this is read here, it's asking whether 1 year is a good indication of the next year. And it would be goofy that the rankings would completely reverse themselves. So we would expect that if there's a relationship, that somebody who does well in year 1 would do well in year 2. So if there's a relationship, it would be a positive one. So that's why I wrote the alternative hypothesis that way. The test statistic is exactly the same as we had with Pearson's. So except that we're using an RS, so the R is calculated differently. But otherwise, it's exactly the same formula. And the usual kind of stuff here, if this were the classical approach here, right? You would say, here's a t-distribution. We've got 10 racers, so we're looking at a t with 8 degrees of freedom. And this is upper tail right there. So we'll put an alpha of 5% right there. And we have 1.86, just like the very first problem we did in this unit. All right, so if your t star turns out to be greater than 1.86, we would reject HO. Alternatively, of course, you've got the p-value approach. And the p-value says that simply if the p-value is less than alpha, then we would reject HO. All right, let's do some calculations here. Now, this is what you do. Remember when we were taking a look at the Kresko-Wallace test, what we did is we looked at all of the data together. So we would look at all these together and then rank them from 1 up to 20 in this case. We don't do that here. What you do instead is you consider each treatment or each column separately, right? Each variable separately. They're not treatments. And so you consider year 1 and you rank them from 1 to 10. Now, they're already ranked that way, so it's not a problem. When we get down to the next problem, we're going to have to change that. Then we do the same for year 2. So they're ranked separately from year 1. And they're also already ranked here. So this is already set up for you. Now, there's 2 columns next to that, the difference and then the difference squared. Actually, that should say difference squared, not DI2. That's just the way it came across here on my iPad. Oops, lost my page. Okay. Let's get back there. All right, so what you do then is you go across each row, and let me just change colors here to say blue. Oh dear. So you go 1 minus 2 is equal to minus 1. 2 minus 4 is equal to minus 2. 3 minus 1 is plus 2. 4 minus 3 is plus 1. 5 minus 6 is minus 1. 6 minus 5 is plus 1. And we've got minus 3, 0, 0, and plus 3. And if you've done it correctly, it should sum to 0. So just take a quick look up here. It looks like we are good. Yeah, we're good. Okay. So they all sum up here then to 0. But we want to square these, so that gets rid of the problem that some are negative and some are positive. So minus 1 squared will be 1, and then minus 2 squared is 4. 4, 1, 1, 1, 9, 0, 0, 9. And then we add them all up and we get 30. So that's your di squared value. So now what we do is we go back to this formula up here, which is also in your formula book. So this guy right here. And then we're going to stick that into the t formula afterwards. So this is all part of step number 4, the calculation. So the RS then is going to be 1 minus 6 times the sum of the di squares. So in our case then is 30. And it's already squared. It's already sum of squared values over n, which in our case is 10, times 10 squared minus 1. So it's kind of a goofy looking formula. It's kind of like the Kruskal-Wallis. Where did that 12 come from? Where did this 6 come from? Remember that this 6 is not a sigma, it's an actual 6, and that the sum of the di squared is just this number down here, the 30, right? So you don't have to square that again. 10, of course, is the number of pairs, number of racers in this case. You should end up then with a number between negative 1 and positive 1. Whoops. Right? So if you're outside of that range of negative 1 to positive 1, then you've made a mistake somewhere, and you want to go back and correct that. So that seems to indicate a fairly strong positive relationship. Let's continue on here and we'll calculate the t star value. So that's going to be equal to 0.818 times the square root of n minus 2, so 10 minus 2, over 1 minus 0.818 squared. And that comes to 4.025. And that is going to be reject HO. Let me just go down here, and that's way over here. So here's your 4.025. And the p-value, you could look that up on the table. It's way out there. But that would be a T dist right tail, 4.025, 10 degrees of freedom. And that comes to about 0.002. So it's really quite far out there. And that means that we would reject HO, and there is a significant relationship between the two. Significant positive one. All right, let's do this last one here. We're just going to push through and finish off this unit here. So we're taking a look at the height-weight problem using Spearmans Test. And so rho S, Spearman's rho, is equal to 0 against the alternative. If you take a look back at when we first did this problem, we hypothesized that if there's a relationship, we would expect it to be a positive one. All right, same test statistic, except that you're using RS. And of course, your critical region is just like it was before. This is upper tail. Ooh, this is terrible. Let me redraw that. Okay. Ooh, that's not much better. So here's a T with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 minus 2 is 8 degrees of freedom. This was upper tail. Right, and that's based on the sine of HA, and that was 1.86. So just like the problem above, actually. Or with the p-value approach, we would say, or if the p-value is less than alpha, reject HO. Okay, now, the one thing that we have to do in this one is that the data have to be ranked. And so we take a look at this. I've actually designed this so that the x's are all in order, so you can just simply go down here. And so this is going to be 1, 2, 3, 4, 5.5, 5.5, right? So just like you do in Kruskal-Wallis, except that you do in one column at a time, one variable at a time. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then over here, we've got 1, I'm just going to give you the numbers, 1, 4, 2, 3, 5, 6, 10, 7, 8, and 9. If you go down, you'll see how that works. And 95, of course, is the smallest. The next smallest is 130, so it gets a 2, then 140, and so on like that. All right, so it's really important, really, really important, guys, to remember this, that in a Spearmans test here, a common mistake that people make is they don't change those original interval variables into ranks. And so you can't go 56 minus 95 because you'll end up with a really big number here. What you do is you change them to ranks, and then it'll be 1 minus 1 is equal to 0, right? 2 minus 4, so 2 minus 4 is equal to minus 2. 3 minus 2 is equal to plus 1. And so on all the way down here. So we're going to have here, this is 1. Where are we there? 1. Then we've got positive 0.5, 0.5, and then minus 0.5. And we've got minus 3, we've got plus 1, and plus 1. And if you've done that correctly, then this should sum up to 0. Let's just check that out. 3, those cross out, and those cross out. Yeah, good. Now, what we're going to do is we're going to square each of these. So 0 squared is 0, minus 2 squared is 4, 1, 1, 0.25, 0.25, 9, 1, 1, 1. And when the smoke clears, you get 18.5. There you go. All right. Let's figure out the RS value. So RS is equal to 1 minus 6 times the sum of the DI squares over n times n squared minus 1. So in our case then is going to be, and remember this 1 is on the outside, it's not in the numerator. So it's equal to 1 minus 6 times 18.5, already squared, over, I guess it's 10 again, right? 10 times 100 minus 1. And that comes to 0.888. Remember when we first did this, back on page, what was it? C4, the R turned out to be 0.896. So this is pretty close. We've changed them into ranks so that they're not going to be exactly the same, but you should get something which is fairly close. Now, let's take that and stick that into a T-star formula here. Let me get back to the right page. Okay. And so we're going to have RS times the square root of n minus 2 over square root of 1 minus RS squared. So in our case then, that would be 0.888, that's positive, right? Times the square root of 10 minus 2 over the square root of 1 minus 0.888 squared. And that comes to 5.46, which is actually pretty close to what we had when we did the Pearson test. Now, that is way out here. right? And so we're going to end up rejecting HO, and that shows us in that there's a significant positive correlation between the two. The p-value is almost 0. All right. And you could find that with a t-dist right tail. There is an RT function for that. 5.46. And then 8 degrees of freedom. And you'll end up with something almost 0. Of course, it's not exactly 0, but it rounds to that. So there's a significant correlation. Last part of the question here says, which is a better test? Is it Pearson's or is it Spearman's? Well, because the two variables are interval in nature, we would say that Pearson's is preferred, but because normality fails, and actually I'm not sure if it does, I haven't actually done an Anderson-Darling test, so let's assume that it fails. So if the normality condition fails on either the x or the y, or both, then actually Spearman's is the better test to use. So that's what we would say here. Go with Pearson's because you get more information, unless the conditions fail, in which case you would go with Spearman's. And that ends the lesson. And Unit C. Remember that you want to take a look at the problems at the end on page C10 and C11.